At solving systems by graphing. A system of equations is a collection of two or more equations with the same set of unknowns. In solving a system of equations, we try to find values for each of the unknowns that will satisfy every equation in the system. Here is an example of a linear system of equations. This system can be solved either by graphing, substitution, or elimination. Now, when solving systems of equations, there's different types of solutions that we will come across. The solution to the system of equations is the point that satisfies all of the equations. This point will be an ordered pair. You will encounter three types of possibilities for solutions. The first type is one solution. When we have two lines and we draw them, the point at which they intersect or cross is the solution. Thus, the solution to this graph that you see is the ordered pair 1, 2. So this is one type of the solutions that we may come across, where it's one solution, which again is just one point or one pair. The next type that you might see is no solution. And for no solution, the things that we look for no solution is that we look for parallel lines. These lines never intersect. Since these lines never cross or touch each other, these lines are what we would say, if we drew them, would be no solution because there is no point of intersection. And parallel lines, something to make note of, have the same slope but different y-intercepts. Okay, they have the same slope but different y-intercepts. Now, the third type of possibility that you'll come across when solving systems is infinitely many solutions. These are where the two lines that you graph overlap each other. They are the exact same lines, okay? And since the lines are on top of each other, there are infinitely many solutions. There are infinitely many points at which they touch, and thus this is how we would represent infinitely many solutions. Now again, when looking for this, something that you may look for is that these lines have the same slope and the same y-intercept. So those are the two things that we're looking for in the equations, that they have the same slope and the same y-intercept. Notice the slight difference between the no solution one. The no solution, they had the same slope, however, not the same y-intercept. So there's that slight difference there. Now, when solving systems of equations, the first step is always to get both equations in whatever form is easiest for you to graph. The different types of forms would be slope-intercept form, point-slope form, or standard form. My suggestion would be slope-intercept form. That tends to be the easiest one to graph from, and it helps you out when doing the other ways of solving systems with substitution and elimination. So once you get them in that form, then you're going to graph both of them. Graph both equations on the same graph, and once you have that, then you look for the solution. Again, based on what we just saw, if the two lines happen to cross or intersect, then we're going to state the point of intersection. What is the ordered pair? If the two lines happen to be parallel, then obviously we would state that it is no solution. If the two lines happen to be the exact same line, then again we would state infinitely many solutions. So let's go through some examples and try to work through how to solve systems of equations and what to look for. For our first example, it says, what is the solution of the system graphed below? So we're given a graph with these two lines, and they want to know what is the solution. Well, again, this is a system. There are two or more graphs being represented. In this case, there are two. And so what we are looking for, the main thing is that point of intersection. And I notice that the 2 points intersect right here at this particular area. This is the point 2, -2. Thus, this is the solution based on this system. So again, looking for that point of intersection. So a similar problem we have is this, again, what is the solution of the system being graphed below? When we look at this, again, we're looking for that same thing. We're trying to look for that point of intersection. But what I'm noticing is it looks like they are parallel lines. Now, how could I notice that? Well, one thing is I could recognize the slope in each, and I'll show you that. If we find two particular points on the graph, doesn't matter which direction you go, but in this case, I'll go up. So up 1, 2, 3, and I'll go left 1, 2. So I have rise over run, and that's the slope of this first one. Do notice that the graph is falling, and because the graph is falling, I know that it has a negative slope. So the slope for this first graph is -3/2. Now I do the same thing for the other graph. I find this point here, and I see another point right here. Same idea, and I'll do the same way. 1, 2, 3. 1, 2. Same idea. This one has 3/2. Again, the graph is falling from left to right, so I know the slope is negative. And this shows me that obviously the slopes are the same. Being that the slopes are the same, but their y-intercepts are different. This one has a y-intercept at 1. This one has a y-intercept at 7. Being that they have the same slopes, but different y-intercepts, this lets me know that the solution to this is actually no solution. These two graphs will never cross. So now we're going to change it up a bit. And this time we're going to be given systems of equations, and they want us to solve it by actually graphing. So the previous one, we were given the graphs and asked for the solution. Now we're given the equations, and we need to solve it by graphing. So as I said, based on our steps, step 1 is to get them in the form that is easiest for you to graph. If you notice here, both of these are in slope-intercept form. As a little reminder, slope-intercept form is y equals mx plus b. M being your slope and b being your y-intercept. Now, once we have it in this form, which we notice that both of these are, then the way to do it is always to start with your y-intercept and then do the slope. Now, a quick reminder for slope, just in case you need it, that whenever the slope is positive, then you're going to be going up and to the right. Now, if the slope is ever negative, then you're going to be going down and to the right. So that's kind of a side note of what's reminding us of how to graph. So let's graph the first one. If I look at the first one, I have y equals x minus 4. So I know the slope in this particular thing is 1, which can always be written as a fraction, 1/1. And I know its y-intercept is -4. So to graph the first equation, I start at -4. Remember, the y-intercept is always on the y-axis. y-intercept, y-axis. So at -4 on the y-axis, that is where I'm going to start. Then I do the slope. Well, notice that this slope is positive, and based on our little reminder, that means we're going to go up and to the right. So from my starting point, I'm going to go up one and right one, and up one and right one, and up one and right one. Now, when doing systems, it's good to continue as far as you can go, so that way you get a good amount of points. Now, do remember, you can do the complete opposite. And what I mean by that is I went up and to the right, so I could do the complete opposite of that, which would be down and to the left. And this would give me the full array of my graph all the way across. Then I can go ahead and draw my line through. So that's the graph of our first equation. Then we want to graph the second equation. Again, this is y equals -5/3 x plus 4. So, again, noting the two things that I need, the slope in this particular case is -5/3, and the y-intercept is +4. Now, for this one, again, I always start with the y-intercept, y-axis. So right at +4, that is where I'm going to start. Now the slope in this case is negative, and based on our little reminder, negative means down and to the right. So we would go down and to the right. So from my starting point, I'm going to go down 5 and right 3. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3. And so once I get a good amount of points, and remember, you could do the complete opposite. I can go up 1, 2, 3, 4, 5, and left 3. Now that would take me off my graph, but again, you could go that direction if need be. And so once I have enough points, I can go ahead and draw my line for it. Now again, the whole idea of graphing these systems and looking for the solution is where the two lines intersect. And so I notice that both lines intersect right here at this particular point, and that is the point 3, -1. And so thus, the actual and final answer to this particular problem is 3, -1. Okay, so this is just kind of the extra work. The final thing that you're looking for is the actual solution. This is the solution to the system of equations. Now again, this we could plug in to check our work. If we plugged in 3 for x and -1 for y and plugged it into the first equation, if it made the equation true, then we know it works, but we do have to check both equations. If it just works for one and not the other, then we did something wrong and it's not the solution. So again, this is graphing a system of equations. And again, you're just plotting the two graphs and seeing where they intersect. And again, if they don't intersect, you're looking for the other two possibilities. Is it no solution or is it infinitely many solutions? Let's try another one of those. So again, the same type of problem. We are given two equations and they want us to solve the system by graphing. So same deal. I'm going to graph them exactly how I graph the other ones. So I'll start with the first one. And again, this is just me kind of breaking it down a little bit more for you. So I take the first one. I notice that it has a slope of -2. Again, this can be written as a fraction. And it has a y-intercept of +3. So we always start with the y-intercept. So at +3 on the y-axis, that is where I start. The slope is negative, which again, if I look at my reminder, that means down and to the right. So I'm going to go down 2 and right 1, and down 2 and right 1. And you continue this again. You want a lot of points to make sure you really get a good array of points because we're looking for the intersections, remember? And again, you can always do the complete opposite, which would be up to and left one, and up to and left one. Once you have enough points, go ahead and draw your line. Then we'll graph the other equation. So we have y equals negative 2x minus 3. So in this case, the slope is negative 2. Again, we can write it as a fraction, and the y-intercept in this case is negative 3. So again, we will start at the y-intercept, which is at negative 3 on the y-axis. So right down there, negative 3 on the y-axis. The slope is negative, which reminds me to go down and to the right. So I'm going to go down 2 and right 1, and down 2 and right 1. And remember, I can do the opposite. Up 2 and left 1, up 2 and left 1, up 2 and left 1, as far as I need to go. Once I have enough points, I can go ahead and draw my line. Now, one thing I notice about this, and sometimes you can notice it right at the beginning, the slopes happen to be the same. However, their y-intercepts were different. And in this case, when the slopes are the same and the y-intercepts are different, well, I know these graphs will never cross. These are parallel lines. And because they're parallel lines, this has no solution. So that would be the answer to this particular problem. Okay? Now, the ones that we just tried happen to have equations both in slope-intercept form. So both of them were already in slope-intercept form. Now, in this particular case, notice how one is not in slope-intercept form and the other is. So based on that, those steps that I told you to take, the first thing that I would do would be to get the other one in slope-intercept form. Okay, so I'm going to take this negative 5x minus 5y equals to negative 15, and I am going to put it in slope-intercept form. That way it makes it easy to graph. Well, again, slope-intercept form is y equals mx plus b. So the idea of this is to basically get y by itself. So in order to get y by itself, I have to use inverse operations. So in this particular case, I will add the 5x to the other side, giving me negative 5y is equal to, now again, I'm setting it up for slope-intercept form, so it would be best to write the x part first and the other part second. Now we're almost there, but y needs to be completely by itself. So in order to separate a number from a letter, this we have to do by its inverse operation of division. So we go ahead and divide by negative 5. When we do so, we get negative 5 divided by negative 5 is a positive 1, so that's why we're left with 1y. 5 divided by negative 5 is a negative 1, and so I'll just write it as negative x, but if you prefer to write the 1, you can. And negative 5 divided by negative 15 divided by negative 5 is a positive 3. So now I have my equation in slope-intercept form. In this particular case, and we might as well just graph this one, we have the slope, that's negative 1, the y-intercept, that is 3. And remember, we can write that as a fraction, the slope. And so I start at positive 3. The slope is negative, which means down and to the right. So I'm going to go down 1 and right 1. And I'll do that as far as I can. And I'll go the opposite direction to make sure we get our full line. So that was the first equation. Then I'll go ahead and draw the second equation. Again, that was y equals 6x plus 10, where m was equal to the slope, which is 6, or 6 over 1, and b is our y-intercept, which is a positive 10. So on this particular case, I do have to go off my graph a little bit, so I'll make a little bit more room. 1, 2. Okay. So in this particular case, we do need to start at the y-intercept being at positive 10. So all the way up here at positive 10, that's where we're going to start. The slope is 6. Now, in this case, we would go up and to the right. Now, that doesn't make too much sense to me because if I go up 6 and right 1, I'm going to be way up here off my graph. So I can always do, again, the complete opposite. That would be down and to the left. So I'll go down 6, 1, 2, 3, 4, 5, 6, and left 1. And down 1, 2, 3, 4, 5, 6, and left 1. And again, you can do it as far as you need to go until you get your graph. Once we have our two graphs, again, the whole point of this is to look for where they intersect. That is the solution to our equation. I notice that this is the point of intersection, and it is the point -1, 4. Thus, this is the solution to my system of equations. So notice it was just a little bit more work than the last one. The last one we had, the last two, we had them both in slope-intercept form, and so we were just able to just graph right away. In this particular case, notice we only had one of them in slope-intercept form. The other one was not. So we had to do a little bit of adjusting first to get it into slope-intercept form, and then we were able to graph both, again, looking for where they intersect to be our solution. So we have another one very similar to it. And again, I noticed that the first one isn't quite in slope-intercept form. This actually looks more like standard form. And this one's a little bit different. So it's kind of something new to us. But again, let's try to do what we can. Let's take that first one and try to put it in slope-intercept form. So we're going to take that first one. 6x minus 2y is equal to 2. So again, I'm trying to aim for slope-intercept form, which is y equals mx plus b. So again, I got to do that rearranging to get y all by itself. So I go ahead and subtract 6x to each side, giving me -2y equals -6x plus 2. Again, notice how I'm trying to set it up for that slope-intercept form. Got to get y by itself, very similar to the last one. We're going to go ahead and divide everything by -2. In doing so, we get y is equal to, well, again, -6 divided by -2 is a positive 3x, and 2 divided by -2 is a -1. So now we finally have that first equation in slope-intercept form. We might as well start graphing it now. So we have the slope, which is equal to 3, or 3 over 1. And the y-intercept is equal to -1. So again, whenever we have something in slope-intercept form, we start with the y-intercept, which is -1. So right on the y-axis, right at -1, that is my starting point. This is a positive slope, so that means up and to the right. So from my starting point, I'm going to go up 3, 1, 2, 3, and right 1. And I'll continue that again as far as I need to go, trying to get as many points as possible, and we will go the other way. Now for the second equation, it's not in slope-intercept form fully, but this is a special case. Notice how there is no y. So when we just have x is equal to a number and there is no y, this is what we call a vertical line. Okay, this is a vertical line. So the idea of that is this is where x is equal to 3, but again, this whole vertical line all the way straight up and straight down, every single thing right up and down on here, this would represent our vertical line for x is equal to 3. And I notice that right there at the top, that is where my 2 points intersect. It looks at 3, 8 happens to be that point of intersection. And so this is the solution to my system. So be a little bit careful with these ones. That is a special case. The other type you might see, just as a little side note, the other one that you might see is like if it was just y was equal to some number, okay, where there's no x. And when there's no x, this is a horizontal line. Okay, it would be left to right. Okay, if we were to plot it on this graph, we would go right here and it would go straight across left to right, right through where y is equal to 1. Okay, that would be a horizontal line. So that's the other special case that you may end up seeing. Okay, let's do one last one. So our last one, notice neither of them are in slope-intercept form. And so in this particular one, we're going to have to do a little bit more work. Still, the very end process is the same, but the whole idea, let's get them both in slope-intercept form. So I'll take the first one and work with that. So we have 8x minus 16y equals negative 8. So again, trying to get it in slope-intercept form, I subtract the x to get it to the other side. I get negative 16y equals negative 8x minus 8. Go ahead and divide everything by negative 16. In this case, we get y is equal to, now in this is negative 8 divided by negative 16, which actually gives you a positive 1/2 x. And then the same thing here, plus 1/2. Okay? And we can graph it. Let's start by graphing it. M is equal to 1/2. That is our slope. The y-intercept in this particular case is 1/2. A little bit tougher to do, but we will do it. And so from here, again, this is where I start, where y is 1/2. Well, right here, halfway between 0 and 1, that is where y is 1/2. Okay. Now this one's going to be a little bit tougher to see, and we'll work through it as we can. But positive slope means we're going to go up and to the right. And so I'm going to go up 1. Notice how I'm going up to the next half, and then over 2. And then up 1 and over 2. And up 1 and over 2. And up 1 and over 2. We do the same thing. We go down 1 and over 2. And down 1 and over 2. And down 1 and over 2. Until we get a good amount of points to represent the line that we are drawing. Then I go ahead and do the second one, again trying to rearrange it into slope-intercept form. We'll bring it down all the way over here. And so adding the 14x to the other side, I get 28y is equal to 14x plus 14. I go ahead and divide by 28 to both sides. And in this case, we end up getting y is equal to 1/2 x plus 1/2. Well, interesting. That looks to be the same exact equation. Notice how these two have the same slope and the same y-intercept. So I don't actually have to graph another line because that line is the exact same line. If I were to, it would just be graphing it right over the top of it. So when they both have the same slope and the same y-intercept, well, in this case, they are the exact same thing. So our solution in this particular case is infinitely many solutions. Every single point on that line is a solution. Okay, every single point on that line is a solution to this equation. Because the two intersect at every single point, they basically are right on top of each other, so they touch at every single point on that line. This is why we would say infinitely many solutions. So again, this is how we solve systems by graphing. I hope this helped you out, and have a wonderful day.